And hello, welcome back to our turbulence modeling videos. And so we've kind of covered the LES, the last bit of LES in the last video. We saw that, even if you use a constant Prandtl number of 0.9 for a whale model, you could still get roughly decent results with this kind of differences between the Nusselt and the friction coefficient for mixed convection, both aiding and opposing mixed convection. Because opposing mixed convection is in general a little bit more challenging to simulate either way. You can see the big difference in skin friction coefficient because of like for the same mesh size, that there's more turbulence in the opposing mixed convection side, so you got to make the mesh a little bit finer. Okay, so as compared to the aiding mixed convection side. So that's something we have to take note of in general. And now we want to talk about a little bit more interesting things, such as the hybrid models. One example is the K omega SST IDDES model, which in this case has been shown to predict the aiding mixed convection parts pretty well. And it doesn't do the opposing parts as well because, again, the same mesh was used in the aiding mixed convection as the opposing mixed convection, as compared to the opposing mixed convection. So let's move on to DES, which is a hybrid of both. Now, first thing first, you may be asking what Prandtl number to use. We kind of covered that. Usually we have 0.85 in the boundary layer, and recommended value is about 0.4 or 0.5 for LES style grid or LES grids in the center. We saw from dynamic models that we have a turbulent Prandtl number of almost 1 near the boundaries and closer to 0.5 near the center. Well, of course, actually the most important Prandtl number to talk about is the Prandtl number near the boundary layer, because the boundary layer is probably the most important part that talks about heat transfer, especially near the wall. So that's the thing we have to take note of for this kind of situations here. Of course, if your medium is generating heat, if your fluid is generating heat, for example in the fire case, then you may want to take note of this dynamic Prandtl number models as well. But that's for the special case of fire or reacting flows, where you have some kind of reaction producing heat. So that becomes more important in the bulk flow if your flow itself is producing heat. Otherwise, most of the heat transfer is supposed to take place in the wall, and the heat transfer should take place in the wall. So the place where the wall, the area in the vicinity of the wall is something more important perhaps than selecting the right Prandtl number, or having a different dynamic Prandtl number for the wall side and the free shear zone. Okay, so there are a few papers using DES models for channels. So for example, you have complex geometries like rotating cooling channels. So you can imagine a concentric cylinder or something like that, where the channels are rotating relative to one another. There are also dimpled surfaces, heat transfer for dimpled surfaces. So if you want to think of dimpled surfaces flow, they actually reduce the friction coefficient a lot, and while generating the turbulence, similar to how your golf ball is designed. They have this dimpled surface to reduce this drag coefficient on them. That's why they can fly further. And of course, in this paper, the K omega SST IDDES is used. Okay, so for IDDES flow in this upper situation, Prandtl number of 0.9 is used. Okay, and then even if you left it at a constant 0.9 for IDDES, for this Prandtl number range of 0.171 and 3, tested against some empirical correlation, and is found to be somewhat reasonable. Very similar to how these results are compared against DNS, except of course for opposing flow convection. Okay, so this is for dimpled flow. Okay. However, this Prandtl number equals 0.9 actually causes some log layer mismatch in the boundary layer. As you have seen before in the earlier papers, the gradient of the log layer is the same for the temperature, but the intercept is different. So if you take a look closer to what we were discussing previously, let's see. Yeah, if you remember this graph, for example, you will have your experimental data showing this log layer in brown. Then you have some sort of over prediction. Sometimes you have models that do over prediction in the Reynolds average Navier-Stokes, the RANS models, which over predict. They do this. They actually have the same gradient, but the intercept is different. So you kind of shift the curve, the log region curve up and down. So this is in a log scale of y plus, and that's how we have this log layer mismatch that often happens for RANS models. And of course, you want to use a RANS model near the wall for DES type models. So this is a very common thing when you have this log layer mismatch. How can you deal with this log layer mismatch? Okay. There are either you use a intermediate value. I mean, you try and have a dynamic Prandtl number, or you have a wall function of the Prandtl number where the turbulent Prandtl number changes as you go further away from the wall, or you can try and adjust the Prandtl number in the wall function in your CFD code and the free shell region separately. OpenFOAM seems to have this capability, but I mean, nothing's perfect. You still have to validate it against some experiment or some DNS simulation. The other way to solve it, okay, is to use another model altogether, to come up with another model. Okay, so this model is called the production limited DDES model, which has fairly good agreement, whether it's in aiding or opposing mixed convection. The error percentages are on the order of 5%. So this is perhaps the best for this case and for this given mesh size. Of course, that you can actually tweak your IDDES model in the opposing mixed convection side to try and get a better result, because I mean, it was said in Ding's paper that the mesh size here is too coarse because there's so much turbulence there. You kind of need to refine it a lot. But if you want your Reynolds, the RANS model to be able to take care of this opposing mixed convection as this PL DDES is doing, then you have to kind of tweak the RANS wall function, the RANS treatment near the wall, so that it can treat this opposing mixed convection. So this, you can see, is pretty challenging. Okay, so that's the PLDDES model. Okay, so this I mean, if you're interested and you want to try and recreate this experiment, here are some notes. I mean, the mean Reynolds number, the mean flow Reynolds number is about 4494. Prandtl number is 0.71. This is very characteristic of air. The Grashof number for this mixed convection, because we have natural and forced mixed convection, forced convection together. The Grashof number is 9.6 times 10 to the 5. By itself, it will actually just represent. It looks like it's more or less a what do you call that? It could be quite representative of some natural. Yeah, it looks laminar. I mean, it's small, but I can't just say the details off the top of my head. But it's pretty small as compared to the Reynolds number. So remember our Richardson number, as you can see here. The Richardson number for this case was actually about 0.048. Or if you want to go through those calculations, 9.6 times 10 to the 5 divided by 4494 squared, you'll be 0.04753. so it's very small. It shows the relative importance of natural convection in determining, as said before. Okay, and why remember why we have this discrepancy again is because in opposing mixed convection, the turbulence generated is way more than aiding mixed convection, so it's a lot more challenging to simulate. You need a finer mesh to resolve turbulence in opposing mixed convection. So that's from Ding 2020. Okay. All right. So if you don't want to do all this resolution and do the brute force way by making the mesh really fine and having your LES resolve things, of course having LES resolve things is going to be a little bit more universal. If your mesh is fine enough, you can capture. If your mesh is fine enough, I mean your LES could resolve most of the turbulence in that region, and that's fine. But it'll take a lot of computation power, as you would know, and you would have to kind of be careful in how you size your mesh. There's some technique to doing that. But if you want less computation power and still have this kind of mixed convection phenomena well simulated using the Reynolds model, there was actually yet another kind of DDES model called the production limited DDES, also invented by these same authors. It was built to counter this boundary layer problem. Okay, so you have this temperature lock layer mismatch in a boundary layer, and the way that it was countered was to formulate a slightly modified model for the K omega SST DES. So they tweaked it a bit to try and make the wall functions, the temperature model match better. So it's worked for this natural convection case. I mean the not natural convection, opposing and aiding mixed convection. It has some of the best results for the skin friction and Oztop numbers here. And of course you should take note, this is a very simple setup of a channel flow, which is a 3D version of flat plate flow or couette flow. Not flat plate flow, couette flow, where fluid is flowing between flat plates. Okay, so yeah, here we are, PLDDES model. So I just start here. It is built on the K omega SST or the BST, the baseline model, not SST model. So this is K omega SST without the production limiter. Okay, if you remember, from the K omega SST there is a production limiter. So you have it somewhere here where you have a production. Remember, your production term is a minimum of some tau ij del uj del ui del xj, and then you have 10 times the dissipation rate being your maximum turbulence production here. Okay, so what happens if you have this limiter around? Let's say you have for natural convection cases, because you have this limiter, it doesn't provide as good. Okay, it doesn't provide enough turbulence in this region, right? You have natural convection going up, or rather you have this turbulent mixed convection, right? So there's a mean flow going up here, so it should be like that. Mean flow going up here, then this natural convection going down. There'll be lots of mixing in this boundary layer, lots of turbulence production. Okay, so you need to take off this cap in particular. Okay, you need to take off this production limiter cap. Why was this production limiter cap here in the first place? It was actually because this K omega SST model was designed for aerodynamics modeling, and what they found was that, hey, in the stagnation regions, there's too much turbulence, too much too much turbulence generated. There's too much turbulence generated here in this stagnation regions where you have a U infinity, and then this is a sphere. Of course, it's a sphere, and then U infinity is impinging on the sphere, it's going against the sphere, and there's a stagnation region and there's too much turbulence there. That's why they have this artificial limiter there. Of course, when you have this artificial limiter, it means that, hey, it's only calibrated for this aerodynamic kind of flow and not universal to this turbulent production. Okay, it is not universal. So again, this production limit PLDDES model is catered very specifically for this kind of heat transfer mixed convection flows, and is good especially for this turbulent heat transfer in the turbulent boundary layer. Just want to re-emphasize this point that there is no such thing as a one-size-fits-all turbulence model. Each of these have its strengths and weaknesses, and I mean, theoretically, if you have infinite computing power, you can do this DNS all the way through, but unfortunately that's not true. So you have to use different turbulence models for different situations, and the PLDDES model, the production limited DDES model, built by Wang and Chen, these are perfect for this temperature lock layer mismatch, but they may not do as well for aerodynamic flows. So you have to give and take there. Okay. So remember, you have this production limiter. There's PK here. Oh, I already copied and pasted it down. So if we limit, we cap PK at 10 times the dissipation rate, or epsilon. Okay, if this is the epsilon, the way I define epsilon is this. For literature, it'll be slightly different. So yeah, you have this production limiter term here. Okay, so now that you've taken off this production term cap, what happens now to the, how do you then control excessive production of turbulence? So instead of limiting production like this, an artificial function is instead used to clip the turbulent viscosity. What do I mean by that? It means that I want to actually so-called have imposed artificial maximum. Okay, artificial maximum. Impose an artificial maximum on nu t. So so we start from the point that nu t is actually some function of k and omega star, where k and omega star is defined as such, where omega is the epsilon, the dissipation rate over the turbulent kinetic energy, and that's the turbulent frequency. And then fr is this new function over here. There's a new weighting function, we call it fr. We have some function. Okay, so what does this function look like to kind of cap this nu t? Okay, so to cap the turbulence over here, especially in the near wall regions, we have this fr function. This fr function actually it minimizes it has this artificial cap, so it's from 0 to 1, artificial turbulence cap from 0 to 1, and this turbulence viscosity in the near wall region is then blended with the turbulence viscosity in your LES region. So remember, as with all DDES models, I hope you're familiar. If not, please go and watch some my old former DDES videos. These are, you have a turbulence viscosity, which is usually a blend of the RAN side, the Reynolds average Navier-Stokes, the RAN side and the LES side. So this one will more closely resemble, more pertain to the RAN side. Okay. So again, similar to a lot of the ways we dealt with model stress depletion before, again there are some shielding functions. So over here we have a blend between, I think, the wall wall side viscosity, and then of course this one is in the free shear zone. Okay, so you have this function which is which goes between 0 and 1. So this function here is the minimum of this LC over LT. LC is the okay, this is the characteristic length of the cell, and LT is the characteristic turbulence length scale. Okay, so characteristic length of the cell, this is a cube root volume, hopefully you're familiar, and some random constant, I mean not random, model constant in the front. LT is a turbulence length scale. This one's quite familiar. It should be somewhat of a mixing length. Okay, and FD, it's a mix of the blending functions, very familiar, you'll find in IDDES. Again, these guys actually make a reappearance from IDDES model. So of course in FD2 you can calibrate your constants to be something other than 14, which is here, and 3, which is here, and yeah, so you can calibrate them to be something else. But all of this, the way you change this, you deal with this model turbulence in the boundary layer, that's all you're doing to change from the IDDES model, the K omega SST IDDES model, to this PLDDES model. So I'll stop for now. Thanks for watching. I'll see you guys next time. Bye bye.